So what I'd like to talk about today is how we can use nanoscale spectroscopy to study atmospheric corrosion. And first, some words about what atmospheric corrosion is. I mean, you have all seen it. You've seen it in the church roofs in Munich. This is a church in Stockholm. This is a Statue of Liberty. First it was brown, then the copper started to corrode. It became green, which is kind of nice color. So this is outdoor atmospheric corrosion. We can also have it indoors, where it can, for example, damage electronics, as you can see up there. So it's an important part of corrosion. A few percent of the gross national product is lost every year in the world due to corrosion processes, and atmospheric corrosion is an important part of that. So then just a short introduction to what's actually going on. So this is not corrosion in a liquid, but still water plays a really important role, because on every single metal surface, for example in this room, outdoors and so on, there's an ultra-thin layer of water. It's like maximum 10 monolayers of water. If you reduce the relative humidity, it just goes down so it's even thinner. So humidity plays a very important role. So if high humidity, the corrosion goes fast. If the humidity is lower, it goes much slower. So this is a copper surface, and then you can see this ultra-thin layer of water on top of it. And then you have some gaseous compounds coming in here. It's, for example, oxygen, it's formic acid and water. We have worked a lot with formic acid as a model compound, and the reason we chose formic acid and that is because that's a compound that is given off from like wallpaper, from the ceiling, from the floor, and so on. So it's a very common corrosion promoter in indoor environment. So when we talk indoor, yeah, it can be this room. Things can corrode. Electronics in computers can corrode. We can also, of course, have more significant indoor corrosion if we go to a chemical lab where we work with a lot of acids. Then we're going to have a very severe indoor corrosion. The background to this project is a very thorough study that Salman Husseinpour did. He's in the audience here actually today. He was my PhD student a number of years ago. He worked with a number of different techniques and investigated the atmospheric corrosion of copper very carefully. For example, we used vibrational sun frequency spectroscopy. It's a really surface-sensitive laser spectroscopy technique to determine how protective monolayers, only like one molecular layer, could protect copper. We could see how the orientation and the order of these molecules were changing upon exposure to corrosive gases. We also used infrared reflection absorption spectroscopy to determine which kind of corrosion product that formed in situ, and also how fast they were forming. We used quartz crystal microbalance to determine nanogram masses of these corrosion products. And we used X-ray XPS to also determine the nature of them. We also use some other techniques. The thing is that all these techniques give macroscopic information. So IRAS probes like 1 or 2 centimeters. In some frequency spectroscopy, the laser beam is like 500 micrometers. So we were always wanting to also probe something on the nanoscale, because corrosion commonly doesn't occur homogeneously over the surface, but it occurs at certain spots. So why does it start at a certain position, for example? Why does a protective film break down at a certain position? So that's why we wanted to do nanoscale spectroscopy as well. Well, I talked about that we can use monolayers to protect the copper. Does it really work, a monolayer? Well, if you look at the left photo, that's bare copper exposed to formic acid in 20 minutes. And you can see that it's quite heavily corroded. We covered also in the right picture copper with hexane thiol. So that molecule is like 2 nanometers thick. And you can see after 60 hours, the copper looks like brand new. So essentially no copper oxide cuprate has formed due to this single molecular layer. So now I want to go to our studies that we have done the last years. So we started from macroscale, then we go to microscale, and then we end up in the nanoscale. So first, if you look at this piece of copper that we have studied, so this is a piece that is like 2 by 2 centimeters, so it's quite large. It was exposed to 80% humidity and an atmosphere with formic acid. Of course, it's also nice to do experiments like in the real world, like in an office or like in a museum, for example, or in a lab. The problem is that there are hundreds, thousands of different types of gases there. So you don't really have control over what's going on. So that's why we have performed a number of our studies in a model atmosphere, just using relative humidity and formic acid to kind of simulate a simple indoor environment. So this piece of copper was exposed to this. Well, you can clearly see with your eyes that the corrosion is not homogeneous. You see you have a lot of bluish area in the middle, which is copper oxide, and then the sides is not so much that actually has happened. And then we take an infrared reflection absorption spectrum, also called grazing IR, grazing incidence IR. And essentially we have two corrosion products that we form in this case. To the far left, we have copper oxide, or cuprite, it's also called, at 650 wave numbers. And we also have copper hydroxy formate that gives rise to a strong peak around 1600, and it's also the OH bond gives rise to a peak around 3570 wave numbers. So those two are the corrosion products that are formed, and our interest was to see how they are developing by time, and also how these two are distributed on the surface. So then we want to go a bit further down, a bit smaller scale. So first of all, this is a photograph of this copper surface, and you can see the small circle there that is magnified to the right here. So this is a light optical microscope image. And here you can clearly see also when we look at this smaller scale, the scale bar there is 20 micrometers, that the corrosion is quite inhomogeneous. We have like a brown sea where the copper is not so corroded, and we also have these blue islands where obviously more corrosion has occurred. So clearly, just looking at with the IRAS with this, where we have this resolution of 1 or 2 centimeters, we essentially probe the whole sample, is not enough to be able to say what is really happening, what's going on the nanoscale. So then we did some IR microscopy studies. So this is conventional IR microscopy, so we just focus the beam. In our instrument, the best lateral resolution we can have is around 5 by 5 micron. This was taken at a larger area, so this is taken by 50 by 50 micrometers. And you can see that this kind of looks like what we saw also on this wider area. I mean, a normal IR microscopy has been a great tool in many corrosion studies, but as you can see in this case, we essentially get the same spectrum as we did with IRAS for the 2 centimeter area. So it didn't help so much in this case. You see the cuprite and you see the copper hydroxy formate. So then, of course, we wanted to go nanoscale, and that's when we were really happy that we had this nano microscope. So this is our setup, the instrument we are using. So we have 3 kinds of lasers. We have QCLs, so we can do single wave number imaging in some areas. We have 1 laser in the middle. That is a broadband laser. It's covering the range from around 650 up to 2200 wave numbers. And we also have this last laser going from around 2200 up to 4000. So yeah, it's not like a synchrotron, but still we can cover quite a large range from 650 up to 4000 wave numbers, although we have to do it in steps, of course. So this is the instrument we have used now in the studies I will come to. So what can we do? Yeah, so this spectra was taken at NeoSpec a few years ago. So you can see that here we want to probe this corrosion product, the copper oxide and the copper hydroxy formate. Copper oxide at 650, just at the cutoff frequency for this laser that was used. The FM imager is 1 by 1 micron, so it's really small. We took some spectra, different places. You can see A and B, the red and the green ones, show some copper oxide there. The other ones, like C and D, they show copper formate, quite clear, spectra agreeing with macroscopic spectra. E, you see, well, there is a chunk up there, but obviously, as you can see here, it's not copper formate. But this really gives us the ability to distinguish where are the corrosion products located at the nanoscale. And with this last laser then, we can of course also probe the OH bond of this one. And you also see the broad band here, which is like a mixture of water in the film and also hydroxyl ions. And now I'm going to talk about a bit more in detail about these studies. So you see up to the left, we have a light optical microscopy image. You see there's some white spot in the middle. So we zoom in on them. So this white circle that you see here, that's the same area. In the same image, you can see that there is some structure. We also took an AFM image, which you see down to the left. There you also see some hills and you see some valleys. Obviously something has formed. And then we wanted to see where this copper formate actually located. So we took a QCL single wave number image at 1590 wave numbers, which is the maximum absorption of this one. And you can clearly see here that these red areas, that is where the copper hydroxy formate has been enriched. So now we can start to say where these are located on the nanoscale. But we were also interested in what's going on if you could go deep into the material in the Z direction. So then we also did some focused ion beam on this one. And we took some SEM images and we did some EDS to see where the copper hydroxy formate and the cuprite was located. And it turned out that the cuprite was located further down and that the copper hydroxy formate was formed on top of the cuprite. So the cuprite is forming faster in the beginning and then the copper hydroxy formate starts to form. And I also always think it's good to complement an image with spectra to really know what you are looking at. So this AFM image and the single wave number image are the same as from the last slide. But then we also took some broadband spectra of these ones to really make sure that it is the corrosion product we are looking at, that we think we are. So the spectra here are taken at the points over there. You can see at some points, the top four ones, we have a significant amount of copper formate. But then at the C, where we don't really have any chunks, there is essentially no copper formate. You see that there is, also at the four bottom spectra, there are some small peaks. So we think maybe actually that they have a really thin copper hydroxy formate layer covering the whole surface. Then we have also these chunks, the larger one that are growing at certain positions at the surface. So this is clearly not homogeneous corrosion, so that's why we were so happy that we could study it on the nanoscale. So that was an image of the copper hydroxy formate, 1600 wave numbers, but we also had the cuprite. With our laser back home, the problem was we could not really probe it so detailed because simply we didn't have enough energy. But then the Neospec Atticube, they advertised this new OPO laser last fall semester, and they were kind enough to do some measurements for us. So we could actually also map the copper oxide at 650 wave numbers. So this is an image. You see these structures. Again, you see this C behind it. Here you can see a map of the copper oxide, 648 wave numbers. This is really low, so I think it's a very nice complement to the other one. And if we look at 1600 in the exactly the same area, we can map the copper hydroxy formate. So if you look a bit more in detail in this one, you can see that you have, if you look at the face images, the ones at the bottom, you can see where we have a lot of copper oxide, the red areas. We don't have any copper hydroxy formate and vice versa. So here we can clearly tell where the copper oxide is located and also where the copper hydroxy formate is located. It seems like if you also look at the topography, that the copper oxide is like a C, and these chunks again is the copper hydroxy formate. And then, as I said, we also wanted to protect the copper with some layers. In some applications, you can have really thick films. In some applications, you cannot have thick films. So we were interested in what can we do with single monolayers. So we used thiols, octadecile thiols, like 2 nanometer molecule. We used ODPA, which is the molecule over here. And we did this in the self-assembly process. We had an ethanol solution with these molecules. We just put down our copper surfaces. We waited some time, and then the molecule assembled on the surface. And the reason we thought this could work was that these molecules, they are hydrophobic. They have a nice packing. We have measured with some frequency spectroscopy. So that's why I thought this could make a good barrier. If you look at this one, you see the bare copper after 20 hours, the red one, it has corroded quite a lot. If we dip the copper surface in ODPA 1 second, 1 minute, well, not much really improves. If you put it in 10 minutes, 1 hour, expose it to 240 hours, so 10 times more, you can see that it's actually working quite well. So then we start to reduce the corrosion. So if we look at the images here, you can see that in all of these ones, well, we reduce the corrosion, but it's not really perfect. The spectra reveal, both for ODPA and for ODT, that we seem to have some copper formate over the surface. And also, if we take some images, we can see that we have still some chunks. And what's interesting is, I don't have time to go to the mechanisms, but it seems like ODPA forms larger chunks that are not so spread out, but ODT forms much smaller chunks. And that is something I could give another talk on, but that's another occasion. So these copper surface corroded, and well, that gave us a lot of nice spectra and images, isn't it nice? But of course, the whole point was also to do something to see, can we protect the copper in a good way? And yeah, so this is the last thing I want to show, that yeah, it actually managed to do it if we pre-oxidize the copper surface. Just a few nanometer, and then we put on a single layer of ODPA. So a few nanometer of cuprite, 2.5 nanometer ODPA. You can see here the blue spectrum and the top spectrum. So like after 200 hours, we didn't form any corrosion products at all. See, then we got a lot of nice images where we had the corrosion, but also we managed in the end to make some really good corrosion protection. So just 2 take-home messages. We were able to probe local corrosion from around 650 to 3600 wave numbers, and we also managed to use organic monolayers to protect the copper. So this is done by Weijie Zhao. He graduated in our group in December, and also collaboration with Professor Emeritus Christopher Legraf and also Dr. Miriam Böhmler, a former NeoSpec employee. And also I'm grateful to Adrian and Klaas in NeoSpec Atocube, who made those images for me at the 650 wave numbers. And also the China Scholarship Council, who financed Weijie's PhD, and to the Ulla Enquist Foundation, who made it possible for us to buy this instrument. So thank you very much.